Hello, everyone. Thank you for coming. My name is Grigor.
My name is Robert.
And today we're here to give you a short introduction into data science with a particular focus on k-means clustering and link analysis. So my name is Grigor. I have a bachelor's in mathematics and computer science from the University of California, San Diego. I also have my master's in data science from Lewis University in Chicago. I worked as a software engineer at Northrop Grumman for 3.5 years. And more recently, I have been working as a web developer at Intuit for 1.5 years.
So my name is Robert. I graduated with a bachelor's degree in mathematics and economics from Fairfield University. After graduating, I was picked up by Cypress Resources as a subcontractor for the United States Air Force, working as a data analyst in their auditing. Afterwards, I went to Live Casino and Hotel, which is located near Baltimore, Maryland, originally starting off as a data analyst for the marketing department, but eventually switched over to the position of business intelligence developer.
So thank you for coming. Like I said, this is to serve as an introduction. So this presentation is primarily for people that are interested in data science and may not have so much experience within it. This is also for engineers and IT professionals who work closely with data scientists. Maybe perhaps you don't know everything that they talk about, and so this will help develop some of the fundamentals that come along with it. Also, this is very applicable to businesses and governments around the world who use data science on a daily basis for their analysis.
So first, I'm going to be starting off the presentation by discussing about k-means clustering. But first, let's just talk about clustering as a whole. Clustering is a branch of techniques based around trying to find like-minded attributes between elements and creating specific groups together. K-means clustering is an unsupervised learning algorithm that looks at n dimensions and tries and places them in k groups, where the number of groups is specified by the user. So for example, we're going to see an ideal clustering in the bottom right-hand screen. Each of the colors is a different cluster, because ideally, based on these data coordinates, we are going to assign it 3 clusters. And in order to do this, we look at the sum of squares distance and try and minimize it through the usage of the Euclidean distance formula. So just to talk about the Euclidean distance formula real quick, it is a formula that you use to measure the distance between 2 points in space. So let us look at points x and y. This is the difference between y and x. However, just keep in mind that k-means can be done in any number of dimensions. So for example, if n equals 20, or we have 20 dimensions, then just imagine those x and y coordinates having 20 different subpoints that indicate each of their positions within each part of space. So now I want to move on into an example of k-means clustering itself. I'll be using Alteryx, which is a data analysis and data cleansing platform. But as stated earlier, what's interesting about k-means clustering is that the user can specify how many clusters they want. However, we need to find the optimal number of clusters. So for example, here is a demonstrated version in Alteryx. We have all of our selected fields, and we can standardize using the z-score or unit interval. The reason you would do a standardization is because in k-means clustering, your numerical fields can have vastly different scales, and those different scales can impact the weight and add bias to your data. So for example, let's look at age and median. Age will be commonly defined between a range of 0 and 100. Meanwhile, income could go anywhere from 0 to 1,000,000. The income will be more heavily biased, and they'll put more emphasis on it because it has a larger scale. So those are 2 standardization methods. Z-score applies the central limit theorem, which takes the data coordinates and turns it into a standard normal distribution, which would have an expected value of 0 and a standard deviation of 1. The unit interval takes every point, minus it by the minimum, and divide by the difference of the maximum and the minimum. You can also specify the number of starting seeds, because with k-means clustering, it'll look at each of those clusters and assign them individually. By increasing the number of starting seeds, you're going to add more repetitions of the algorithm, which would increase your accuracy, though it does come at the direct trade-off of increasing your runtime. So once you run this formula, which again could be done in Alteryx, but also R, SQL, Python, there are different options. You're going to have these different box plots, such as the adjusted rand index and the Kolinsky index. These are box plots that lay out different quartiles. As you see, these small white dots are indication of outlier data. Generally speaking, the higher, the further up, the more compact and the less amount of outliers, that is going to indicate your optimum number of clusters. So in this specific example, preferably Kolinsky index is used because Kolinsky assumes normal distribution, and as we previously stated, by standardizing z-score with central limit theorem, everything is a normal distribution. And here we see that 2 is compact, but it's a little bit lower. 4 has a huge amount of outliers, but with 3 having a minimum outliers and the highest score, 3 would be your ideal number of clusters used in this specific example. So now that we have found that the optimum number of clusters is going to be 3, we can configure a k-means clustering. So we select all of our fields, standardize with z-score, select, we're going to be using k-means rather than k-medians and neurogas. These are different clustering techniques that we won't be covering today, unfortunately. Specify the number of clusters and starting seeds. And now on the right, you are going to see this is how Alteryx visualizes the k-means clustering. All of your different data points within your space are going to be assigned those different numbers, and those numbers are going to be each of your different clusters. So all of the 2s are going to be indicating that you have cluster 2, all of them 3 will indicate cluster 3. In general, this is a breakdown of k-means clustering in multiple n-dimensional space, though you can modify the visualization in order to make it a bit more appealing and easier to understand. Now, however, while k-means clustering is a great data analysis technique, it does have a lot of limitations that we cannot address, that we have to address. First and most notably, it cannot work with categorical data. So just to clarify what categorical data is, categorical data are non-numerical elements that we are going to assign numbers. For example, colors. Let red equal 1, black equal 2, white equal 3, etc. Or another case, let m equal 1, f equal 2, u equal 3, those kind of examples. The reason why this doesn't work with k-means clustering is because we're assigning them arbitrary values. This makes the Euclidean distance measuring that k-means clustering relies on becomes effectively moot. You can work around this with the usage of k-modes clustering. However, k-modes clustering is a lot more complex than k-means clustering. Another error you have to address for is making sure all your data sizes are equal to each other. So suppose we have 5 different fields, A, B, C, D, and E. Each of them have 100 elements in them. However, E is only going to have 80 elements. This negatively biases and skews your data because those 20 missing coordinates cannot be measured with the Euclidean distance. And if we cannot properly measure the Euclidean distance, then the k-means clustering doesn't work exactly. Finally, while k-means clustering is a relatively simple method, it does take a long time of execution, especially if you increase starting seeds, bootstrap replicates, increase the number of dimensions, or want to try and find 5 clusters. The more clusters, the greater the runtime. My average calculations when Alteryx, when I was doing about 10 dimensions and 3 clusters, was looking at 30 minutes. So it can take a long time. However, you can try and minimize and increase efficiency. But this is just one form of data analysis and clustering. Next, I'm going to go over to Grigor, who is going to be covering link analysis.
So hey everyone. So like I said, link analysis is just one of the many data analyzing techniques that you can use. Like k-means, this can also evaluate patterns and relationships between nodes. The primary difference is that when it comes to link analysis, most of the time you're representing your data as a graph. So nodes as they are seen, it's important to remember that they also represent people, companies, and in some cases transactions. So some of the common applications are, for example, law enforcement. So by having this link analysis, you can actually understand patterns that exist or should not exist, and that can help you uncover things that might happen in the future. Another thing is anti-fraud. So like I said, if there are certain transactions that should not be linking with one another, but they are happening, that could be detected and flagged. So sometimes if you're leaving the country and you didn't tell your credit card will call you and say, hey, we don't think this is you, you shouldn't be here. And another one is security intelligence. So most nations internally and internationally use link analysis to uncover threats to their national security as well. So I wanted to come up with something fun to kind of get everyone's attention. One project that I did was link analysis of dolphin communities in Florida when I was working on my master's degree. What this allows us to do is try to figure out which dolphin communities actually interact with one another, but more importantly, figure out if these communities actually exist. So just because you have a bunch of data that you collected in one area doesn't mean that they actually form any meaningful groups with one another. So if you look at this data set that we have, you'll notice that it has 62 nodes. Each node represents an individual ID. So we have 62 dolphins that we're actually looking at, and they form 159 connections. These connections can range anywhere from 0 to 61, because a dolphin can't form a connection with itself, so that's why the n-1. So what does the data actually look like? Most of the time when you're getting this, you might get it something as simple as a 2-column data set. And in this case, each column just represents an ID, and most of the time you represent it as source and target. Where is it going and which direction is it flowing? So when you look at rows, rows will represent the relationship between one another. Like I said, it's an adjacency list format, but you can also have it in different ways, which I'll talk about later. The important thing is that once you have this data, link analysis allows you to visualize it in a graph. And the graph has many applications that we will talk about. This is an example of the adjacency list that was used in this project. So adjacency lists, they look like unordered lists. So there is no particular order to the rows that you consume, but it's important to maintain the source and target relationship amongst the rows. Each unordered list describes a set of neighbors. So oftentimes what you'll have is an ID, and then sometimes you can represent that as a subset. So the set could either be empty or contain all of them. Adjacency matrices are also something that's very common. They're really, really nice for when you're trying to show directed graphs. So graphs that always have to go in a specific direction. Most of the time you don't have this one-to-one. So if me and Robert are friends, then we share a mutual connection. But if let's say I see a celebrity, I have a relationship with that celebrity, but that celebrity has no relationship to me. Also, it's important to note that even though you can use adjacency matrices, if you use them for undirected graphs, what you'll have is a symmetric matrice. So what that means is you'll see that here, across is a diagonal of zeros, because again, you can't have a relationship to just yourself. You have to have a relationship to someone else. But if it's undirected, then it's going to look exactly the same on the top or the bottom. Here's just a visual example for those of you that might not be familiar what directed and undirected graphs look like. So it has to follow a specific flow. When it doesn't, it can go up or down. The tool I used for this specific project was called Giphy. Giphy is a very fantastic open source software. It's made by French developers, and it's primarily made in Java. I would highly recommend anyone that's interested in link analysis to go use it. It can seem a little intimidating, but I have found this amazing resource, DerekGreen.com. He has a fantastic tutorial on how to use this step by step. And this is what the visualization looks like. So you have an adjacency list. You want to represent it as a graph, and this is what the graph can look like. Now, this graph isn't accurate when it comes to the distance between IDs. So just because two dolphins in this graph are next to each other, that doesn't mean they're actually forming a community. So that's important to understand when you're actually looking at these graphs. What is the bias that was intended with it? And that can be uncovered using a modularity report. A modularity report simply tells you what is the groups that are existing within your data set. So when it comes to this, you could see on the horizontal line, each one represents simply the number, so how many exist. And then the vertical axis tells you how many belong to the group. And this brings us to a very important idea in graph theory, the graph theory idea of centrality. So centrality tells you how important a node is. So if you see a node in the center in some graphs that have biases, that doesn't mean it's the most important node. And the way we define that is, okay, is this important for maintaining relationships between groups? Is this the bridge that connects one group to another group? So there's two types. There's betweenness and closeness. Betweenness tells you how many times someone had to traverse this to get to one node to another in the shortest path possible. Closeness simply tells you how close something was to each other. So for this example, we went with betweenness because that was the whole point, trying to discover the relationships that dolphin communities have with each other, if any. So once you take the modularity and the betweenness, what you can do is you can color the edges. And these edges are, again, the relationships from one to another. So this tells you how many exist. And then you can weight them using the betweenness centrality. So the nodes that are weighed the most are the biggest in this graph on the on the right side. And so those we would define as being the most important ones. So let's say you are a marine biologist. You only have 5 tags to put on these dolphins. Which dolphins do you want to put them on? You want to put them on the ones that create the most meaningful relationships. And these are the results. So what we found out was that there was actually 5 groups of dolphins existing off the coast of Florida. Some of them are usually the same size, around like 30% of the total set. Some of them are much smaller, so we can consider them to be almost negligible. And what we uncovered was that the average length between these was actually 3.35. So that just means how many dolphins you have to go through before you get to the next one. And the final results were not so exciting. We actually found out that these dolphins don't create any meaningful communities around one another, even though there are dolphins that take it upon themselves to create many of these interactions between one another. But there are a lot of other use cases for this. So for example, everyone, I assume, has a Facebook. You can go download your own personal information off of Facebook. It comes in a nice JSON format file, and you can plot them in a link analysis. So what you'll see here is all your friend groups. So sometimes you have all these friend groups, and they don't talk to each other, but they talk to you. So you're the bridge that connects your friend group to another friend group. Same thing with Twitch, which has a big community of streamers, and oftentimes viewers on these websites will stay within their groups. They don't like to go outside of their groups.
So in conclusion, both k-means clustering and link analysis are 2 different types of analysis. Data science is a huge field. You're going to be presented a wide variety of different data sets with different constraints asked by your boss or supervisor. Rather than limiting yourself to one method, it's best to know a variety of methods so you can have the right model and the right approach for whatever task or whatever data set you're being handled. We hope that this introduction to these 2 different methods can help show you some different ideas on how to approach your data whenever you want to group or classify or analyze data.
And thank you.
Thank you.
Any questions?
I have a question about k-means clustering.
Yeah.
You mentioned that there is a method to choose a minimum clusters, right? In your presentation, but there is also a method, elbow method, right?
Yeah, there is.
So is the logic same or it's not a logic?
Unfortunately, that's just a method of analysis I don't have a ton of experience with, so I can't give you a great answer.
Okay.
I'm sorry.
Because I haven't heard about your method, but I think it may be better than elbow method, because elbow method usually shows more than one result. So yeah.
Yeah, it probably would be then, because it's giving you multiple results. It's just, again, something I don't have a ton of
Got it.
user experience with.
Thanks.
In my experience, elbow method is actually somewhat accurate, but again, it's kind of like an eye test. You kind of just see the way it goes and you make your own distinction. The numbers don't differ much past a certain point, which is, I think, what you were alluding to, which is his method gives you a little bit more accuracy.
Yeah, that's what I was asking. Yeah, thank you very much.
So you were talking about the communities, right? One of the questions I want to ask, in direct graphs, how can I do communities, like discover communities in directed graphs?
In directed graphs?
Yeah, because I know that most of the communities are in undirected graphs.
Yes.
Directed graphs is really hard to find communities in. What methods we can use so we can detect communities in directed graphs?
So there are several other techniques that you can use. Unfortunately, I haven't used any of them very recently, so I would have to brush up on them. I'd be more than happy to talk to you after this presentation so we can get more information about that. I only prepared something for undirected. I'm sorry.
Okay. Just another question in graphs. For example, if I'm in a group, like in my friends, I want to find the leader in that community.
Okay.
What can I use? Like, should I use closeness, betweenness, or should I use only betweenness? Centrality, degrees, what exactly?
Right. So I think it's important that when you're looking at it to try to look at the diameter of the graph as a whole. So how wide does it actually go? And the centrality is the most important part. When it comes to betweenness or closeness, that is a distinction you yourself have to make. But I would, off the top of my head, think that if you're looking for the leader, The leader is the person that is at the intersection of most of these groups. And so I think you would still want to use betweenness in that case.
So it's like the bridge.
Yes. Yes. So if I go back to this, the leader would be the biggest one in this group. So 37, for example, you would see him as the guy that brings people together.
Any other questions?
For undirected graphs, at least for your research, was there any distance associated with the edges, or is that insignificant for this analysis?
So there was distance involved in this. So at the end, the results that we found was what is the average path that you have to traverse to get to this. So the distance in this case was about 3 to 4. So that's how far you have to go.
3 edges?
Yeah, so like, 3 nodes. So the edges connect one node to another. Yeah.
Okay.
Yeah.
So the dolphins weren't friends?
The dolphins don't like to make friends with people outside of their own groups, unfortunately, which is very difficult if you're a marine biologist trying to figure out where they all go. Unfortunately, that's what was discovered from that data set.
You know the reason?
You start getting into psychology at that point.
Yeah.
I have a question about Dolphin analysis as well. Your data set was quite small, right? 56?
It was only 62 nodes.
Okay. So is there any new data set that gives you significant analysis for this method?
I think it's just the more you have to work with, the better you get. I've seen sometimes people have reports that only have 35 members within it. You really don't want to get anything smaller than that because the data becomes more difficult to distinguish between each other.
Okay, so what was the significance level of your analysis?
The significance as in terms of the pool that we had to work with?
Yeah, the result, like you get like 60, your result you said that dolphins don't make with like 80% of
Accuracy.
Yes. Okay. So we were able to, within the group that we had, have good accuracy, but it was surprising that they didn't form communities, which makes me think that if there was a bigger data set, there might have been something more interesting to find.
Yeah, okay, thanks.
Yep.
Thank you guys for the presentation. You were talking about not being able to use categorical data for k-means clustering. I'm wondering, I keep thinking about analyzing demographics data. So what kind of method would you recommend for that?
So the method that would be best recommended is k-modes clustering. K-modes is similar to k-means clustering, but by using mode centroids rather than mean centroids, it actually can accommodate both categorical and numerical data. So if you're looking at your categorical data and you also want your numerical analysis combined, k-modes clustering would be the best approach. It's just a bit more complicated than k-means clustering, so it will take a little bit more to understand.
And we're out of time. Thank you.
Thank you.